Module 5, Section 3.4, Present Value of an Annuity and Amortization. Objectives. Objective 1, calculate the present value of an annuity, calculate the payment for an annuity, construct amortization schedules, and develop strategy for solving mathematics of finance problems. Objective 1, present value of an annuity. Present value of an annuity is the amount that should be deposited into an account now at a given interest rate in order to be able to withdraw equal amounts from the account in the future until no money remains in the account. This is a typical example. How much money must you deposit now at 6% interest compounded quarterly in order to be able to withdraw $3,000 at the end of each quarter for 2 years? Present value of an annuity is calculated using this formula. Present value equal to payment multiplied with 1 minus 1 plus I to the power negative n divided by I. Here I is the interest rate per period. N is the number of periods. You also need to notice that payments are made at the end of each period. Let's do an example. Find the present value of an annuity if n value equal to 31, I value equal to 0.045 and the periodic payment is $181. So we make the substitution here. 181 for payment, I value is given. So once we do this on the calculator, we will get $2,994.53. Let me show you how we can enter this in the calculator. So we have 181 multiplied with, it's important that you need to use a parenthesis around the numerator here, 1 minus, again parenthesis, 1 plus 0.045, close the parenthesis, power negative 31. So you need to use the negative key here, negative 31, end of the numerator, so close the parenthesis, divide with 0.045. So if you press enter, you will get the answer, rounded to 2 decimals. Here is another example. How much money must you deposit now at 6% interest compounded quarterly in order to be able to withdraw $3,000 at the end of each quarter year for 2 years? Here the number of periods will be 4 multiplied with 2, which is 8. 4 quarters per year, 2 years. The payment will be 3,000. Interest rate for quarter will be 0.06 by 4. That will come out to be 0.015. Now we have the present value formula here. Substitute. Use the calculator. And we will get 22,457.78. Let's do one more example. eLoan, an online lending company, recently offered 42-month auto loans at 6.6% compounded monthly to applicants with good credit ratings. If you have a good rating and can afford monthly payments of $225, how much can you borrow from eLoan? What is the total interest you will pay for this loan? We are given the monthly payment. It's a 42-month loan, so n value is 42. Interest rate per month is 0.066 divided by 12, which comes out to be 0.0055. So we are asking the question how much you can borrow now, which is the present value. So use the present value formula here. Substituting the numbers, we will get $8,417.37. And this is the amount that we can borrow. To answer the second part of the question, we need to calculate the total payments made. Remember that 225 is the monthly payment. We are making 42 payments, so the total payments will be multiplying these two numbers, getting $9,450. So the interest paid will be total payments minus the loan amount. Loan amount is what we calculated earlier, 8,417.37 When we subtract, we will get 1032.63. So that is how much interest that we will be paying on the loan. Amortization. Amortizing a debt means that the debt is repaid in a given length of time by equal periodic payments that include compound interest. Solving the present value formula for the payments gives us the amortization formula. So if we solve for the payment by cross multiplying, we will get the payment equal to present value times I divided by 1 minus 1 plus I to the power negative n. So here PV is the loan or debt. So let's work out an example. A bank loans a customer $50,000 at 4.5% interest per year to purchase a house. The customer agrees to make monthly payments for the next 15 years for a total of 180 payments. How much should the monthly payment be if the debt is to be repaid in 15 years? How much is the interest earned by the bank? We can solve this question using the amortization formula. So the loan amount is 50,000. That comes in here. So we need to calculate the interest rate per month. So that will be 0.045 divided with 12. So that is how we get 0.00375. So once we substitute in the formula and using a calculator, we come up with $382.50. That is the monthly payment on that loan. The total amount paid to the bank is monthly payment times the number of months, which will be 180, comes out to be $68,850. We only had 50,000 loan, so the remaining amount will be the interest. Subtract 50,000 from the total payments, getting $18,850 as the total interest paid. Let me show you the calculator entry for this. So we have 50,000 multiplied with 0.00375. Then we are going to divide with 1 minus 1.00375 to the power negative 180. So that needs to be within a parenthesis. 1 minus 1.00375 power k negative 180, then close the parenthesis. Next example. A sailboat cost $17,079 and you pay $30,000 down and amortize the rest with equal monthly payments over a 6-year period. If you must pay 8.7% compounded monthly, what is your monthly payment and how much interest will you pay? This is a typical amortization problem because we need to make a 30% down payment. So the actual loan amount is only 30% less the cost of the boat. So we calculate that here. Present value is equal to 17,079 minus 30% of the cost. So we get 11,955.3. So to get the down payment, you multiply the cost by 0.30, which is 30% of that. Now we can use the amortization formula in order to calculate the payment. I value is 0.00725, converting 8.7% into a monthly rate. Total payments will be 6 years, so it will be 6 multiplied with 12, 72 payments are made. So the monthly payment is going to be 213.72. That is substituting back here. So to find out how much interest we are paying for this loan, we need to calculate the total payments. Total payments will be 72 multiplied with 213.72, which will come out to be 15,387.84. So the actual interest paid will be subtract the loan amount. So the loan amount is only 11,955.3. So notice that this is not 17,079. This is the amount of loan that we are taking from the bank. So that comes out to be 3,432.54. Amortization schedule. An amortization schedule is a table that shows the interest due and the balance reduction for each payment of a loan. Here is a typical example. If you borrow $500 that you agree to repay in 6 equal monthly payments at 1% interest per month on the unpaid balance, how much of each monthly payment used for interest and how much is used to reduce the unpaid balance? So we need to calculate the monthly payment using the amortization formula, substituting the loan amount as 500, monthly interest rate as 1%. We will get a monthly payment of 86.27. At the end of the first month, the interest on the loan is 500 times 1%, which is $5. But we are making $86.27 as the first monthly payment. So we need to split this into the interest part and the unpaid balance reduction part. So if you take off $5 from 86.27, what we get is $81.27. That will be used to reduce the outstanding balance, which is 500. So if you subtract that, we are only left with the $418.73 as the outstanding balance at the end of 1 month or just after the first payment is made. Now we need to continue this for the second month. So we have a table here which is telling how the payments are split. For the second month, we are paying $86.27 monthly payment, but we only need to pay $4.19 as the interest. So that means we have $82.08 that can be used to reduce the loan amount. So 418.73 comes down to 336.65. Then you continue like that. At the end of 6 months, we will be amortizing the loan. Actually, there is a 3 cents left over here, which is due to the rounding errors. In reality, the last payment would be increased by 3 cents so that the balance is 0. That means the loan is completely amortized. Here is an example of a typical mortgage calculation. A family has a $155,900 30-year mortgage at 7.8% compounded monthly. Find the monthly payment and also find the unpaid balance after 5 years. So the monthly interest rate will be 0.0065. 30-year mortgage, so we will be making 360 payments in value. So the payment is calculated using the amortization formula up here, and the payment comes out to be $1,122.28 monthly payment. Let's see what is the outstanding balance after 5 years. In 5 years, we will be making 60 payments. 5 times 12, 60 payments are made, and that leaves 300 more payments. 360 minus 60. So in order to calculate the outstanding balance, we need to compute the present value of all the remaining 300 payments. So use the present value formula, which is again up here. The monthly payment is 1,122.28. N value is 300. Notice that we only have 300 more payments to be made. We use the same rate, I, and come up with 147,938.14, which is the outstanding balance after making payments for the first 5 years. Let's look at some strategy for solving mathematics of finance problems. As step 1, we can determine whether the problem involves a single payment or a sequence of equal periodic payments. Simple and compound interest problems involve a single present value and a single future value. Ordinary annuities may be concerned with a present value or a future value, but always involve a sequence of equal periodic payments. If a single payment is involved, determine whether simple or compound interest is used. Simple interest is usually used for durations of a year or less, and compound interest for longer periods. If a sequence of periodic payments is involved, determine whether the payments are being made into an account that is increasing in value, future value problem, or the payments are being made out of an account that is decreasing in value, a present value problem. Remember that amortization problems always involve the present value of an ordinary annuity. These are the formulas that we used in this section. Single payment, simple interest. The future value will be A equal to P times 1 plus RT. Compound interest formula will be A equal to P multiplied with 1 plus I power n, or if it is continuous compounding, we will use the formula P times exponential RT. Notice that I here is always annual rate divided by number of interest conversions per year. I equal to R by M. What is n? N is equal to M multiplied with number of years. We are making sequence of payments. The future value of an ordinary annuity is calculated using this formula. The present value of an ordinary annuity is given by payment times 1 minus 1 plus I to the power negative n over I.